This week we witnessed the discovery of Higgs Boson, a possible clue to the mystery of our universe. Here, Peter Higgs, who predicted the God particle, is being congratulated. Let's take a peek at this discovery. For half a century now, we all took the structure of an atom to be pretty much like this. An atom was made up of a nucleus and electrons revolving around the nucleus. The nucleus was in turn made of protons and neutrons. Protons are positively charged and neutrons are, well, neutral. Protons have mass, whereas neutrons do not. Electrons are negatively charged particles. The question was, what is fundamental? Is it the protons? Is it the neutrons? Or is it the electrons? In fact, it has been found that much smaller subatomic particles called quarks make up protons and neutrons. Well, it is sufficient for us to understand that each proton or neutron is made up of 3 quarks. Till now, scientists believed that quarks and electrons are fundamental. So here is the modern atomic model as we know today. You have protons and neutrons which jiggle within the nucleus. So this is the nucleus out here. Quarks jiggle within the protons and neutrons. So you can imagine this. The electrons which are out here on the edge are revolving around this nucleus, and this nucleus is not static. There is a lot of activity, lot of jiggling happening within the nucleus. But that's not the end. Once the proton accelerator was invented, physicists came up with a number of subatomic particles. We know about 200 particles today. And do you know what is everybody's preoccupation? Every time a particle is discovered, we look for clues whether it is fundamental. An enormous amount of data from experiment is generated on a daily basis. If left, this can lead to chaos. There has to be a broad framework to work and classify new discoveries. So the standard model was developed. It attempts to explain the nature of our world and what holds it together. According to the standard model, we have 6 quarks. Of course, there are more out here. 6 leptons and 4 carrier particles. Many of them, we don't know how many. We have met quarks, but the other 2 are still strangers to us. Well, it is sufficient to know that the best known lepton is the electron, which we all know, and the best known force carrier particle is the photon, which makes up light. But you know what? The standard model is good, but not enough to explain things like how do particles get their mass? Why so? Let's examine this. For example, consider this. A photon is a force carrier particle but is massless. We all know that. Whereas another force carrier particle called W has a relatively considerable mass, that is when compared to photon. Why should this happen? This is where Higgs boson comes in. In 1964, Peter Higgs, a British scientist, predicted the existence of a field which is now called Higgs field. When other particles interact with this field, they mass. The Higgs boson is an imaginary particle which interacts with other particles to endow them with mass. Oh yes, I agree that it is quite puzzling to imagine one particle acquiring mass by simply interacting with the field. Let us watch this BBC video to understand what this really means.
Let me just describe to you what Peter Higgs and his co-discoverers of the Higgs mechanism actually think that this is all about. So I did it for the BBC canteen. Now I want you to imagine that it's the Big Bang. It's just happened. And way back then, we didn't have a Higgs mechanism, okay? And all the particles in the universe were whizzing around at the light speed, okay? So they're going around through the universe at light speed. Now, unless some of these particles have mass, they can't clump together, they can't become stars, they can't become galaxies, they can't become you and me. Right. Everything in the universe that we know would not happen unless they have mass. Now, I need you to help me with the Higgs mechanism. A few fractions of a second after the Higgs mechanism, after the Big Bang, we get the Higgs mechanism. So it's going to go down one.
So just in case you followed it, the presenter there has a few ping pong balls in a tray, and those ping pong balls represent the various subatomic particles. They represent the protons, the neutrons, the quarks, the leptons, like the electrons, the W particles, and a whole lot of things. And what he's doing is he's now bringing in the Higgs field into picture. So he's got some sugar, and he's going to add that sugar onto the tray and just see what happens.
Is he in charge of this? I hope so. Permeating the whole of space.
Can I add this in?
I think we've probably got enough. I don't know.
A little bit more. There you go.
Okay. So now we have the Higgs mechanism permeating the whole of space. And what that does...
So this is where he says that the Higgs mechanism, or the Higgs field, which is represented by a few grams of sugar in our analogy, permeates the whole of space. It's there everywhere. We can't see it, of course.
Is that interacts with our particles. Now, some particles, as they move through the Higgs mechanism, get very bogged down, and they become very, very massive. That's something like a top quark.
So this is the fundamental principle behind Higgs field and Higgs boson is here. Each of these particles out here are interacting with each particle in the Higgs field. You can see that here. Some of them, like this particle out here, this ball out here, they interact so well that they acquire mass, they become heavy, and they sink into the field, so to speak. Whereas a particle like this ball out here, which you see is lightly standing on a mound of sugar, is almost free. You can say that these are like photons which are massless. They have not acquired any mass from the Higgs field. They have interacted with the field, but they have not acquired any mass. We don't know why yet. Let's watch further.
Now the others, they don't interact quite so much, and so they're not so massive. And there's one sort of particle, this one's called a photon, has no mass whatsoever, and that continues to fly off at light speed.
So that's what it was. What he held up there was a photon which has no mass. It just hasn't acquired anything from the interaction with the Higgs field, and it can just fly off. That's why you see photons travel at the speed of light, and nothing else can match that speed.
Okay, but that essentially is what the Higgs mechanism is. They can't look for this directly, they look for the boson at the Large Hadron Collider, and that is one of the particles in the Higgs field itself, associated with the field. So that's what they think they've done.
So, well, that's about Higgs boson and the so-called God particle. I hope you got a glimpse of what the discovery was all about. It's very exciting in the physicists circle, though the layman like you and me might still be wondering what this is all about. This video was made possible by wonderful resources on the web, who put up for free by some of the wonderful people. I thank them for their vision and generosity.